Hey, Jack and everybody, welcome and thanks for joining us as we continue with Autonomous Tech Innovation Week. In case you don't know him, Jack Gold is founder and principal analyst for J. Gold Associates with expertise in many areas, including emerging tech around autonomous. He's also my good friend. So let's jump in, shall we? Jack, we've reached the point where sensors are acting as processors, right? So tell me, what is a sensor today?
That's a great question, Matt. And the fact is that I think a lot of people have an idea of a sensor as being this little 50-cent disc that you put on something to measure vibration or temperature or humidity or maybe focus on my breath to make sure I shouldn't be driving because I had a couple extra drinks. Those are indeed sensors, and there are a lot of those out there. But the truth is that in this day and age, most of what we think of as a sensor is really includes intelligence, not just sensing. And so it's great to be able to take the analog world, temperature, humidity, pressure, whatever, rain, and measure that's happening, but turning it into a digital amount of data that I can actually process and get useful information from and then act upon, that's really the goal. Now, the question becomes, where do you do that? And in the past, what we've done is we've had sensors on these long wires that go back to some central processing unit, or maybe it's a PC, or it's a small box. The truth is today, it's relatively inexpensive and very common for processing power to be actually embedded into the sensor. And so what we're getting off of that sensor is digital data, but pre-processed digital data that we could then do useful things with. So it's not as clean and clear as it used to be. A sensor is this or a sensor is that. Now we're talking about a sensor that's smart and can actually do useful things for us.
Wow. How does a sensor become actionable intelligence, or I'm sorry, the data from that sensor? How does it become actionable?
And that's the key, right? It's all well and good to be able to get data from a sensor, even if it's processed and modified, but then I want to be able to do something with it. So if I'm if I'm monitoring a refrigerator that's storing COVID vaccines, got to make sure that it's 94 below zero. It's all well and good to have a sensor that says, okay, it's 94 below zero, or it's 90 or at 85 or 80, and the stuff is going to spoil. I now have to take that data and say, okay, what do I do with it? I've got to set off an alarm. I've got to get somebody to come in and check out the freezer, or I got to go to a backup system, and maybe there's a second compressor on that freezer if I really want to have redundant systems to make sure that nothing happens. It's got to be actionable. So I've got to process that data. Now, that processing of data can be done traditionally with just an application. It could be done with some sort of data analytics. It could be done manually. We could be sitting in front of a screen and a red light pops up and says, it's now 85 degrees. What should I do about it? And take action. But increasingly, that's becoming a machine learning or an AI type of problem. And everyone throws out machine learning, AI as this. I've got it. Everyone has it. Everyone
Yeah.
uses the term. Whether it's real or not is a whole different issue, right? And so it's really a function of how good a job I do of understanding what that data means and then turning that data into something that's actionable. Now, that should be based on something that I know. So I know that if a vaccine goes below 80 degrees, I'm going to lose $30 million worth of vaccine or whatever the number is. And,
Yeah.
500,000 people aren't going to be able to get vaccinated. That elevates the amount of effort I'm going to put into making sure that vaccine is maintained at the minus 94. If it's I got a couple of pizzas in there and they're frozen for 15 minutes, it's probably not going to make a whole lot of difference to a lot of people.
Yeah.
I can take an hour to perhaps modify that or rectify that, but not so with the vaccine. So that's really important. Knowing how important the data is that I'm getting, knowing what to do with it, and then knowing whether or not I've done it, because you've got to confirm that it's actually been corrected, the problem's been corrected. That's the key to making sensors useful in the real world.
And some of them are right there at the edge. They're not necessarily using the benefit of a data center or a cloud application.
Well, in fact, that's true, and you probably want that for a lot of types of sensors. So, for instance, let's say you've got a sensor on a machine tool that in a factory, and you've got somebody that's stamping metal parts, and I'm standing in front of it. I'm stamping these metal parts, and suddenly my arm goes where it shouldn't. And
Uh-oh.
the
Yeah.
sensor, yeah, well, but this is real, right? Or perhaps if it's not, if you don't want to use a machine tool, how about in a healthcare setting where
Yeah.
I just had I've got a heart monitor on, and something just happened to my heart. You don't have time to send data up into the cloud, wait for it to be processed, and come back. The latency will someone will literally lose an arm or perhaps lose their life.
Yeah.
Autonomous cars, you don't have time to detect that there's a car in front of you. You're doing 40 miles an hour and that car in front of you just stopped, sending that into the cloud and waiting even 30 to 60 seconds for that data to come back. So localized processing, edge processing, is very important to making sure that I can act quickly. Latency is critical in a lot of situations. It's not just about latency either for edge. It's also about privacy and security. The less
Yeah.
data I send into the cloud, the less likely that data is going to be used for bad purposes. And so in a healthcare setting, for instance, you don't want to send my monitoring data up into the cloud where someone can break into it. If it's stored locally and then only sending anomalies to the cloud for further processing, that's a much better process.
Yeah, I think I did a story on the French army deciding they wanted to have everything processed locally just for security. Don't send it back to some place where where it could be hacked.
Right, right. It's
Yeah.
much harder to hack 1,000 points of local data than one central point of a lot of data.
Are there other ways to guarantee reliability or security?
Yeah, there are. Redundancy is very important in many of these situations. So what we find is that for really critical situations, sensors may have two or three. They're not single sensor. They may have two or three sensing nodes. They may have multiple processing capability. Um, an example of this. So I was actually having an interesting conversation with one of the fellows at Intel that's working in their Mobileye division, Dr. Shashua. And he
Mm.
was talking about sensors for autonomous vehicles. There are all kinds of sensors. There are visual sensors, there's camera-based sensors, there's LiDAR-based sensors. We're moving to radar, moving to all different kinds of things. And his comment was a very interesting one. The notion of what's safe in a car for an autonomous vehicle is not so much how you do the sensing, whether it's visual, whether it's a camera base, whether it's LiDAR or whatever. It's what's the mean time between failure. And what he
Okay.
means by that is that if I do visualizing of an autonomous vehicle in a car and my mean time before failure is 13 seconds, I'm going to have a lot of accidents.
Yeah.
If my mean time between failure is 13 years, I'm going to have a very safe vehicle. And so that kind of data is very important around deciding whether you've got a safe system running or whether you've got a system that has all the components but doesn't run very safely. And so it's about redundancy, it's about security, it's about latency, it's about all of the kinds of things that we think about when we're talking about autonomous vehicles, be they cars or delivery drones or robots that are delivering mail in an office location. They all have to have some level of reliability and redundancy in order to be able to make valid decisions so that either people or things aren't put at risk.
Is there a lot of work being done on just making these systems hacker proof?
There is. There's always work being done there, and the problem is, of course, that for everything I do to keep you out, you do something to get in. Right?
Yeah.
It's a never-ending battle.
Yeah.
But there are secure systems for sure. Everything starting with encryption. There are secure systems in the processors that are running attached to these sensors. There are enclaves where you can process data that's very, very hard to get at. They're virtualized machines and hypervisors. I'm getting a little bit technical here, but there's a lot of work done. Thanks. There's a lot of work done to try and make the processing and the data as secure as possible and keep it out of the hands of people who shouldn't have it.
How about this? Can you name some new operations that sensors will soon provide, maybe compared to what we're currently seeing with autonomous?
Yeah, sure. So, I mean, we all know about working on cars. Everyone's working on autonomous vehicles. It's the new guys like Geely in China. It's clearly the folks like Tesla here in the States, and GM and Ford and everyone else are working on it. Those systems right now are level 2. Basically means that I can turn it on, and if I'm sitting in the driver's seat, the car will sort of drive itself, but if there's a problem, I need to be there to supervise it.
Yeah.
It may or may not stop. It may or may not go over the lane or whatever. What they're trying to get to is level 4. Level 4 means I turn it on and I take a nap. And you know,
other things.
yeah, unfortunately, there are people doing that already in their Teslas, which they shouldn't. But you know, that's a whole different problem to have. But that kind of system requires the redundancy that we talked about. The mean time between failure has got to be weeks, months, years, right? It's got to have a lot of processing power. Latency has to be very low, and so a lot of the data has to be processed locally. But it also requires that you have to have a good map of where you're going. Let's say you're driving in a car and you're driving through Boston. Matt, you've certainly driven in Boston.
You would pick Boston, of course.
It's hard enough doing that as a human.
Yeah, well, in an early GPS example, I remember getting to some little place down near Boston College, and it said, take the unnamed street. And I'm going like, dude.
Well, you know the saying about driving about Boston. If you don't know where you're going, you shouldn't be there.
Okay.
So, I mean, that's valid. But the point I guess I was trying to make was, I mean, GPS is great, and it sort of gets us to where we want to go. But the next level for autonomous vehicles has got to be way beyond GPS. Not only do you have to know the street name, you have to know what's on the street. You have to know where the stoplights are. You have to know where the fire hydrants are, where the crosswalks are, where people are apt to run between two parked cars and cross. It's Boston, probably any major city, everyone jaywalks. So there's a lot of data that has to be embedded into the overall system, in addition to the real-time sensor data with the LiDAR and the radar and the visual, you know, the cameras that are going to be required to make autonomous driving not real, but at least safe. And if you don't do that, you're going to have a lot of accidents.
Yeah. And I guess the early examples will be where a robo-taxi follows a certain specified route, where maybe there are some roadside sensors that are talking to the robo-taxi.
Right.
Do you envision, maybe even decades from now that you're going to have that roadside cellular connectivity or whatever the network is?
You're certainly going to have connectivity, and you're going to have low latency connectivity, and it's got to be pervasive. It's got to be available everywhere. That doesn't mean you won't lose connectivity, which is why you still need some redundancy in the vehicle. You've got to have a database that you can rely on while the data, the network is not working for a few seconds. But what I see increasingly important is that we're going to have basically a crowdsourced data network. Sorry, a little hard for me to say today. But if you're driving down the street and you see an anomaly, why wouldn't you broadcast that to me who's 2 cars behind you?
Yeah. That's what Waze theoretically does, I guess.
Yeah. But your C2VX is moving down that path. It gives you the ability to do that. But you're going to have local storage. You're going to have hybrid communications between vehicles and devices. Street lamps may talk to you. Who knows? There's going to be a lot of data, and so the real challenge I think going forward is going to be with all of this immense amount of data. How
Mm.
do you get meaningful insights? How do you get meaningful actions made when you've got to process it all? And where do you process it? How do you process it? Do you process it locally? Do you process it in the cloud, which means you have to have very low latency? Do you process it, in a 3 kilowatt device in your trunk, and then your battery goes for 3 miles?
Yeah.
Uh, it's a significant challenge, and everyone's working on it. But I think
Mm.
we're probably several years away from the real super systems that we all envision happening.
Yeah. I mean, one example I ran across 6 months ago, I think Intel has a chip in development that will look at a parking lot and it knows, like hundreds of cars, and this high res camera will be able to make the decision about whether we should just forward a few frames showing the guy walking between the cars, so that
Right.
it's finding an irregularity and then taking that data, and so that it doesn't all have to stream back to some operator in a remote location.
Yeah, Intel's actually working on some interesting technology. Others are as well. They're calling it neuromorphic,
Yeah,
and it's meant to process data like our brains do.
yeah,
Um, they gave an interesting example the other day. I hope I get these numbers correct. I was on a call with them, and they were saying that a parrot, a parrot that flies around the jungle, has a
yeah.
brain that can get from tree to tree and limb to limb and learn new processes, and uses something like, I think they were saying something like 55 milliwatts worth of power, the equivalent in
Wow.
their brain. Whereas a typical AI processor today can be using hundreds of watts. Even
Yeah,
a small, mobile chip, a Qualcomm chip, still uses several watts of processing power. Now imagine we're having to have 100 of those in a vehicle. How do you power that? So they're looking at things like neuromorphic, which is more pattern recognition, like our brains do, to
yeah,
to to kind of process that data at 1/10 or 1/100th or 1,000th the power of a typical CPU. And we're not there yet. But
yeah.
it's an interesting a way of looking at the problem, and I think we'll make progress over the next few years.
Yeah, they're trying to measure that so that it can be compared to other systems, I think. But that
Right.
that is fascinating stuff. I mean, just the idea. I mean, we've known about neuromorphic concepts for years, and the idea being that the brain has so many neurons that connect in so many different ways. I mean, you
Right.
never even really know how one neuron, and there are millions in the brain, probably billions,
Yeah.
and you never really know how many pathways it has. So we don't even really have a network architecture inside of a chip that can come close to that.
No, you're
Anyway,
right. The brain is an amazing thing,
yeah,
and we, the typical computer processing was built on the Van Neumann theories, right? And those go date back into the 40s and 50s. But the neuromorphics is, I shouldn't say the next generation because it's not going to replace a lot of the CPU stuff that we're doing, but it is another way of looking at processing that will have
yeah,
a major impact, I think, long term on especially visually kinds of oriented systems.
yeah. Well, we only have about a minute left, but I just wonder if you could talk a little bit about the industrial Internet of Things. I mean, do you have any predictions of more growth in that edge device area, from the cloud guys or whatever?
Yeah, I think you'll see actually a huge growth in edge, and it's going to come in a couple of different areas, several different areas probably. One is, today processing power has gotten so cheap that it's very easy for people to put it into small boxes and attach it to industrial equipment, whatever that industrial equipment is. Secondly, 5G, both in public and in private networks, is going to fundamentally change how we send data around because it's so fast, and also because of the low latency. It's about 10 milliseconds of latency if they get everything right.
Yeah,
That's that's great latency compared to what we've got today with LTE, probably an order of a factor of 10 better. The third piece is that you're going to see a lot of edge computing be deployed right in the carrier networks. So think about a small computer box sitting in a cell site tower, or at least at a core center where they talk to several cell sites. All of the networks are moving to virtualized environments anyway, so that means they've already got processors in place that the carriers are putting in place. And now what they want to do is they want to be able to actually charge you to run an application locally for that capability. So you're going to see all of that come into play. You're going to see edge computers in your home.
Yeah.
We actually almost already have that. A lot of the cable boxes that we have in our homes now have a fair amount of intelligence built in, and they can actually put apps into it. Doesn't have the sensor connections yet, but we'll get there. And so industrial IoT, I think, is going to grow dramatically. Smart cities, healthcare, there's a lot of different areas where it makes huge sense, and the payback is really high. I think the problem in the past has been that a lot of people looked at industrial IoT and tried to figure out whether automating a certain process or connecting a certain process made sense from an ROI perspective, and the ROI often just wasn't there.
Yeah.
But
Wow.
if you talk about healthcare, ROI is, I keep you alive. That's a pretty good ROI.
Yeah, that sounds like a good place where we should stop. But thanks, Jack. I really appreciate your big picture view of the tech world. It always makes me feel like I've finally grasped the concept.
Oh, you always grasp the concept, Matt. Thank you. Thanks for having me on. I really appreciate it.